Welcome everybody. This will be the last part or part 9 or task for the walkthrough for task 9 of the 2024 Codebreakers NSA challenge. In the last tasks in task 8, we were tasked with trying to identify the HMAC string used to authenticate the given packet, and we were able to do this by the fact that the uh, shared key that was sent turned out to just be our public key, as their generation of some sort for their private key turned out to be just one, resulting in the incorrect authentication scheme used within the elliptical curve. In this task, this time we're going to try and stop the devices, and with that, I think we'll just jump right in. I'm going to try and leave this or keep this video a little bit shorter than the last one. The last one was a little bit longer. Hopefully, it doesn't take as many parts, if any, more than one this time. Anyways, due to your efforts, the security team at Blue Horizon Mobile finally captured packets destined for another spy device. You highly suspect in their haste to co-opt and gain access to Blue Horizon infrastructure. Wow. The attackers did not carefully implement their own crypto. Can you find a way to craft a packet that, if sent to the device, will stop the agent process and prevent it from restarting? So we have downloads, another packet capture it looks like. Enter the byte stream. Oops. Put me all the way to the top. Enter the byte stream and hexadecimal of the packet payload without the IP and UDP headers. So it sounds simple enough. Let's download this file. Didn't mean to go to that one. Make 9, move, downloads, another capture. Didn't mean to move it in there. Move that into 9. Then we're going to just open it up. See what it looks like. So here we have 2 packets, it appears. The source is the same, and then the destination is the same. If we take a gander at the UDP streams for each, I think they should show up as different streams. Oh, they might not. Oh, they're not. So it's going to show up as the same stream, but I believe, yeah, if we look here, this 6B17 is consistent in both of them. If you remember that, that's just going to be the public key that they send out, so it appears to be that the same setup. The fact that they're the same device is actually going to be interesting for us to try and identify what this data is. But I think we have 2 approaches here. We need to, 1, identify what this data is and a way to send our own data, and then 2, to try and identify an exploit on the process. This part, if this is split into parts, will be focused solely on the reversing of the, not protocol, but trying to identify what's in the data, and then if the video is not too long, I'll just condense this into one, where then, the second part will be trying to identify the exploit and building an exploit payload. So with that, let's actually save this file. I'm going to save as raw, save to data.raw. Close all of this now. We should have a data.raw file. I'm going to actually just split those in half. I'm not sure the best way to do this, so I might just do it in Python. Python 3 f equals open data.raw, do read bytes. F is equal to, we'll do byte b is equal to f.read. We'll just print b. I didn't really check to see how long it was. What's the best way to figure out the length? I guess we could just print the length right now. $768. Could just try to divide it by 2 and walking forward to see when the next couple bytes are. Might be easier just to identify them. If we can quickly identify a K around here. We could try splitting on K 17, see if that works. B.split on this byte. Oops, didn't mean to put a parenthesis in there. Looks like we got 2, which should be right. Nope, we also got the, oh yeah. We'll just set this to A. A is equal to B.split of 1 to the end. Print the length of A just to make sure it's 2. Perfect. Then I'm going to do with open. We'll open up 1.raw as read bytes. Nope, write bytes as f again. F dot write a at 0. We're also going to append the bytes back in that we split on though. 17 plus that. I think that should work. And we can do the same thing with just 2.raw. And set this to 1. Okay, I think that should work. If we do xxd, I did w.raw, xxd w.raw, 6b17, 6b17, d1, yeah, so that looks like it lines up. So that should be our public key. If we remember, the packet is sent as public key, checksum, and then data. So it shouldn't be too bad. I'm going to move w.raw to 2.raw before I forget. Okay, so first we need to try and figure out what's in this data. I had hinted at it last challenge very briefly, but the fact that it's using AES CTR mode for the encryption in the AES implementation actually is the flaw in this part, and that is because if AES CTR is being used and they're using the same public key as the same key scheme as the key and the same counter, they're going to have the exact same round key when they start encrypting, which means that the XOR cipher that's actually used for the data will be the exact same as well. So if we XOR these by each other, I believe it should give us the XOR key. That might not be fully right. Something close to that. But as you can see here right away though, right here at 0x60, not here 0x60 here, you can see that there's a lot of common bytes. So 9546, 954644, 4A, 7664. You can see that they're actually using the exact same XOR cipher. This helps us in the fact that as we had identified the packets in the last challenge, these are going to be null bytes anyways. So that means the XOR cipher for these bytes will be 95464A. That doesn't help us in the long run as these bytes down below, or this XOR cipher shouldn't repeat in the sense that it's guessable. But it does help us in the fact that it's going to be the exact same. We can just prove that we have the correct XOR cipher. Once we have one of them, we should have the other one decrypted as well. So I'm going to just make a directory code. I'm going to do that just to try and keep the codes a little bit separated between all these files so we don't get them confused. Call it decrypt.py. F equals open. Call F1 and F2. 1.raw as bytes dot read. F2 equals open. 2.raw as read bytes dot read. Then we can do something like XOR is equal to the ran or empty. I might actually do a list for x in a length range of length of f1. Do XOR dot append f1. Now both these links won't be the same, or both these files links weren't the same when we saved them, so the XORs will be slightly different. But if we look back here, 1 should be smaller than 2, so as long as we get the majority of 1, it should be sort of fine. F1 at x XORed by F2 at x. And then we can just print this to see what it looks like. Printing it really doesn't give us much now that I think about it, but I'm still going to do it. Bytes at XOR dot hex. Decrypt. We can see something sort of interesting to start up here. We can see that we have a lot of null bytes as we expected. I'm going to actually split this up into chunks of 0x40 because we knew that the all the values sent in are always split up. X in range of 0 to length of XOR by 0x40. And I can just print XOR from x to x plus 0x40. I think that should work. I should be able to subtract that by 40. So now it's going to be split into pairs. So it looks like the first pair is the same. Second pair is different. Same. Just wait, something seems slightly off. I think my estimation is actually off. It kind of lines up. X1, X2, but see, this null byte right here is throwing me off because I'm pretty sure when we looked at them, they weren't the exact same to start. X6D1.raw. Oh, we don't care about the actual first bytes, do we? No, we don't. That's why it's all null bytes. Ha. Okay, so we want to jump in 0x60. Oops, jump in 0x60. The first couple bytes will be the public key. The next one should be the checksum, so it should be different. And then it should actually get to our data. That's where we actually care about. There we go. That looks better. So the first payload has a different differential. So this doesn't actually give us the XOR cipher. This should give us the difference between the two files. We can see, that the differential between the first two files should just be the 6, and then, or the first parameter, so 6. The second one is 1, and then the final one is whatever that data is. So we can actually use this to determine what payload is sent. At the moment, we don't really know what the decrypted value should be. We have from our analysis in the last challenge, we have an idea of what it could be. But since we don't have the public key for this system, since it's a completely different device, we need to identify a way to figure out what data is being sent again, and then be able to figure out what the actual decryption key is, because it'll come in handy later. So with that, I'm going to open up our notes from the last one. I think I saved them somewhere. I think it was an A. Perfect. So we know we have 7 possible commands. The first 40 bytes should be the type. Next 40 should be the number of parameters. The character pointer. Those ones aren't as important right now. They will be important, but at the moment they don't matter to us as much. We have commands. We have 1 is SSH, 2 is HMAC, all those stuff. That looked to be what our data should have been. 0x60 doesn't matter. Public key, checksum, doesn't matter right now either. What we want to try and figure out is what commands are actually coming in, and so we can get the original XOR cipher and use that at a future time. So the way we can do this is that we know that the XOR between these two parts is going to be 6. We know that there's 7 possibilities, so we can just make a quick loop. I'm going to comment this one out because we don't care about printing that right now. For x in range of 1 to 7. 1 to 7? Is it inclusive? I always forget. Not inclusive, so we want 1 to 8. Or actually just do for y in the range of 1 to 8. This will give us the first value, and all we want to do is print or XOR these two out. So say if x XORed y is equal to 6, we'll just print these two out because these are the two possible pairs. We could do this mentally, but it's a lot faster this way, I think. So the possible pairs for these commands are 1 and 7, 2 and 4, 3 and 5, 4 and 2, 5 and 3, and 7 and 1. If we look back at these commands, we can try to identify what possible arguments there are. We can try to figure out what is actually being sent in with this packet. We could try to identify the further data that's being sent along with it, but right now that's not of as importance, I would say. Another thing I'm going to do is print out the length of F1 and F2, as those two are very important when we're trying to identify what these packets are. In fact, that might be the more important part than what we're trying to do in the first part. So what we know is that the first one has a length of 256, and then the second one has a length of 320. If we do quick check, hex of 320 is 140. So right there off the bat, we know that the first command is going to be one of these two, and then the second command is going to be either one of these two, but it's probably not, or one of these 4. It's probably not 6 or 1 though, as those two had a range because we just didn't know if data was sent in, but there's a good chance data probably isn't sent in with these two. So 1 and 6 are kind of the odd ones out right now. In fact, to get 1 and 6, 6 isn't even possible. But to get 1, it would have to be 1 and 7. And there's a good chance that the first one's definitely not 1 and 7, as it lines up too well with these probably. I think other than that, we don't really have much else to go on yet. We had to do some quick math, or not math, just trying to analyze this. So I'm going to copy these to just a temp file. I like to write the stuff down. So 1 and 7, most likely not those, so I'm just going to delete them. If I can. Hello. There we go. 1 and 7. We know that 1 is actually going to be 3 or 4, so it's not going to be 5 and 2, because this first one's going to be right here. So it's 3 and 4. So the second one's either 5 or 2. Well, 2 doesn't line up, so that definitely makes it 5. So that means our packets coming in are going to be of set 3 and of set 5. And that will help us narrow down the last 2 bytes of our XOR key. But what 3 and 5 are, if we remember, 3 appears to set memory. We'll take a quick look at that. We go to command thread, do command, come down to case 3. We can see that parameters have to be at least 2. Takes a string to ln of our s, which should just be our number of our second set of bytes. I think it's our length. No, first one. Command string plus 80. Command type looks like command type actually has to be 1. So that might give us a hint of what our next set of byte is, our next byte. And then we have a string to ln of command string. Oh, it just sets this to 1. So if command type is 1, which is a good chance it is, because otherwise there's no point in calling this function. Command string plus 0xc has to equal 1 as well. So right there we just narrowed down what this entire packet probably is set to. This entire packet is probably set to 3 no bytes, 2 no bytes. I think 2 had 2 parameters, I think. Yep, 2 parameters. 1 no bytes, and then 1 no bytes. So we can check that against the just decryption and see if that lines up well. Count this one out for now. We'll do XOR again, 4x in, I didn't really have to count it all, but I could just count that one line out. 4x in range of that, XOR.append f1 at x, XOR by decrypted at x. Decrypted 1. And we're going to make decrypted 1 up here. Decrypted 1 is equal to the bytes at 3 plus the byte, no byte, times 0x3f plus the byte 2 plus the byte 00 plus the byte 1 plus the byte 0x0 plus the byte 1, nope, not backslash 1, just 1, plus the byte 0x00. So if I did this all correctly, 3, oh, I need to multiply these, times 0x3f, it would actually been easier to just make this a variable and then use that variable. Oh well, 3f times plus plus times plus plus times plus plus times. Okay, then we can come in here. I'm going to then print out, I think I'm going to print out the XOR again, just to see what it looks like. This part we're done with. We already got what we needed. Should probably, oh, we wrote down already, so we don't need to put it anywhere else. I think that looks good. Oh, that's the XOR key. So this is what the XOR key should, in theory, look like. Yeah. Can't really prove right now that that's what the XOR key is. We could take this XOR key. So XOR should now be the XOR key for at least the first 0x to 0x100 bytes. In theory, it should be at least. But we don't really know at the moment what the remaining bytes are for the next part or for the next packet, as we don't fully understand at the moment what that packet is sending. I guess we could look. We knew it was sending 5, I believe. Let me check back here. Cat A. I didn't save it. Did I not save it? Or did I use it put in a different terminal? Oh, I actually didn't save it. 3 and 5 should be the one. 5, remember, sends to navigation. We could check to see what data it might be expecting. Maybe it gives us a hint as what it should be. Command string plus 0xC0 goes into a new function. Oops, not that one. C0 goes into a new function. Takes the string length, does something else with it. We could test. So actually right here, sense navigation service, %s, alternate %s, %d. We could actually test by sending in some test data, see if it throws any errors or what it expects. So here's actually just making a socket call. There's a good chance this is just writing to the socket then. It even calls it right away, so this is probably write of some sort. So call supervisor CE. We still have it open. Nice. Come down to CE. Send to. Yep. Sounds like syscall. So this might actually just be, the first one might just be string length. Just trying to identify how many bytes it's sending. It looks like there's a max length. Okay, go big screen. Thank you. There's a max length of maybe 0x6b. That could also be something completely different. Might not even use it. So maybe it's the max length. So maybe it's like a string end length. Oh, even right there it's calling string end length. So maybe there's a chance that's what it's doing. So I'm just going to say send to socket is what this function does. Send to socket. Come back. This function appears to be a string end length as well. Maybe they're all string end length then. So it looks like this one maybe has a max length of 6, maybe max length of 11, max length of 10 if these are all the same function, which they appear to be. Assuming that's what it's using these param3s for, which it appears to be, if we're trusting that function name. So with that, we could actually identify what length these, or we know now what length these strings should be, so that kind of gives us a hint at what bytes should actually be there. 0x1f, that's probably just more of that stuff. So this doesn't really seem to give us any more hints. We could maybe do some kind of brute force to identify what these should be. It's really hard to fully identify what they should be besides the fact that we know they're strings and they could be any length of this size. So 16 characters, 11 characters, 6 characters, which is if we're trying to brute force all of them at once is a little bit much. Oh, maybe that's not 16, that's just 10. Doesn't look like it's hex like the other two. Or yeah. So, but for now, I think we'll just stick with just looking at the one pack or one payload that we do know about. In fact, we might actually be able to dump some of the data from the second one, as there's going to be some overlap with some of the payloads. As this 5 command should only have one more extension compared to the 3 command, so we should be able to decrypt these two as we have the entire XOR key. So instead of printing this, what if we, I'm just going to copy this command again. I'm going to call one XOR2. XOR2.append F2. And this time we want it just XORed with XOR. That. I'll copy this one. This will print out XOR2. Maybe it'd been a good idea to make these functions, but that's all right. Python 3 decrypt. This looks like a valid ASCII of some sort, so maybe if I don't print it as hex, this will give us a little bit more understanding of what it is. Looks like all numbers, actually. So it actually looks like a GPS coordinate. I feel like I should have one more. That's not 256. Looks like I'm off by one right here. There we go. Looks like those are just coordinates. So the string just turned out to be GPS. So maybe if we can possibly identify what this last point should be. So latitude, longitude, altitude maybe. Maybe I thought alternate meant something else, but maybe alt means altitude. So that'd be probably 0, as a lot of them were all 0. So maybe it just might be a single byte that's all 0. Or just the byte, or just the actual character 0. We'll keep that in mind if we need it. But now we know exactly what this data is, and it actually showed us that the fact that this came out cleanly, we do in fact have the valid decryption key. It looks like everything lines up correctly. It wouldn't hurt possibly to print out what the regular, oh, we actually know what the regular XOR was. We guessed it already, so printing that out doesn't really get us anything. But now that we have the decrypted data, we can try and forge a packet. So trying to forge a packet, we have to try and do kind of the inverse. So far we've been ignoring the first parts of the packet. We've been ignoring the 0x60, but there's good reason for that. The main reason is the fact that the first 0x40 bytes will always be the public key. We want them to think that we sent this from the same source, so the public key, in this case just the curve G, will be what we send. But now we need to try and fix up the checksum. So if we were to modify this packet, how do we modify the checksum? A good way we can do this is if we come back to our script, agent code, I'm going to copy brute. We use brute last challenge to try and identify, move that to code. That actually won't work, so I'll need nano CC and all of those as well. I actually don't need nano ECC. I do need tiny ES though. Tiny EAS and the SHA header. 9 code. I think that's all I need. I'm going to try compiling it just to make sure. Cat brute.c, it should be down here. I just got to change the test.c to brute.c. as.h. Oh, don't need backslash. It's going to be in this current directory now. Oh, it does compile. Running it's not going to work because we're trying to open a public key, which I don't know. That's where we actually come across this. So if we look at brute, we can try to identify what was going. If we just take a quick look at what we were doing, looks like we were using the public key to get the initial SHA-256, as if we look back at the functionality of the decrypt function again, we can try and identify what's happening. So it takes the elliptical curve, gets a shared Diffie-Hellman key between those two, uses that as a SHA-256 key in the AES decrypt, then does a decryption based on HMAC data, or does another SHA on the HMAC data that we had brute forced, does a SHA-256 on the structure itself. If you remember, the structure itself had 2 extra fields added to it with some XOR keys. And then it tries to SHA-256 the buffer we got from AES, and then a final SHA-256 based on the buffer and the data itself again, and then does the checksum. So, looking at our file is actually technically incorrect. I will go back to brute because it's easier to run here. It did correctly run. If we run it, it gives us our secret key. That was the correct answer for the last one. But we actually have unneeded code in here. If we look at this, the elliptical curve stuff isn't actually used at all in the SHA-256, and that's the vulnerability for this, or a misidentification within the crypto. They should have used the elliptical or the shared key at some point within the final SHA-256, as if we meant to do it over here. Then brute, if we comment those lines out, it makes no difference as we're not actually using that anywhere, and we can still get the solution. The reason is just that they didn't use the shared key at all. You can just follow it along. You can check to see where this local 28 is used, and it's not used anywhere else besides being overwritten down here in the final one and in the AES encryption, which we don't actually need because we already have the decrypted AES data, so we can bypass it entirely, which is a plus for us. So the fact that they used AES-CTR with the same key and counter, and that they didn't use the public key or not the public key, but the shared key at all, allows us to totally bypass this step. So with that, we can now try and identify what HMAC key they use to checksum the current data, and try and identify if it's the same as the one we're currently using or if it's slightly different. What's a good way to get it into that form? So I do need CTR. No, I don't. I don't need CTR, I don't need key. AES data we're going to change as we already have the decrypted one in the Python script, so we're going to have to modify that. Data.raw is the same one. It's actually going to be 1.raw this time. We don't need this elliptical curve stuff. And then I think we should just be able to brute force with the exact same command otherwise. We just need to modify the AES data first. So let me come into decrypt, cat decrypt. The fact that it's just single bytes actually makes it easy to change. So we have a 3 here, which is 33. We have a 2 here, which is 32. These should all be zeros, except for this one should be a 1, so that's 31. These are all zeros. It's gotta be, probably was a better way of doing this than what I'm doing. So sorry for making you just watch and sit through the slow, monotonous movement of this. 0, 0, 0, 0. This one is actually going to be 256 in length, so we can just increase that to 100. And then put one more 0x, 31 right here. I'm just going to leave the rest empty because I think it should default to 0. I'm hoping it does at least. And then we can try running that, see if that works. We did not get a hit. So, either I mess something up. So it goes 3 Fs, 2, 1. Number of bytes here looks a little, is that the same? There's a chance it wasn't set to 0. I'm just going to pad this guy out then. Whoops. Yank that. Paste. 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 The fact that I'm mixing hex with decimal doesn't really matter. I could have done this. I probably could have done this all in decimal or ASCII. Probably not the null bytes in ASCII. That's just a pain. That wasn't it. What did I mess up? I think that should be right. I should check to see if that buffer was read incorrectly. Mind the 1.raw is back there. Is it skipping into the correct bytes correctly? Go down to encrypted buffer. Plus 0x40 is correct. That should be the checksum. I think that should be right. AS data. Oh, I'm hard coding 0xC0. Let's change that to 100. 0x40 should be the same. 0x20 should be the same. That should be all good too. There we go. So it looks like we got the exact same key. So whenever they sent us, or the device we first had the key, it looks like it sent it probably globally. So they're all, there might be a chance that they're all in the same key. We can check. You can just run the old one. Looks like they're the exact same key. You could have maybe guessed that or just gone with it that it was, but it's better to actually test it to make sure that it's valid. Now that we have the HMAC key, we can actually do all this encryption stuff in reverse and print it out. Actually, we don't need to really do it in reverse. We can just, I'm going to copy brute to gen.c. We can come down here. We don't need this while loop anymore. Or not while, for loop. Move this down here. set the HMAC, just hard code it. Value is 88538. I'll just leave the sprintf. It's been working so far, and that makes it easier for me a little bit. Correct we don't need, as we know it's going to be correct, so we don't actually care about this. What we do care about is printing it out now. What is the best way? I think get rid of this line. Whoops. Do I have Shift V, not Control V? And then changing this to be just a printf. %20x, %02x of what? Buff? Buff should be our final, I believe. No, buff at x. GCC, we can change brute to gen. So now instead of a brute force script, we now have a generator script, which should dump out our checksum, which 16 characters is not enough, 32 characters. And that should be our checksum for the data we were going to send at this time. But we don't want to send this data. We want to send an exploit. So let's just find a way to overwrite this exploit, and we can rerun this script. So this video currently is around 36-ish minutes. I think we can just append to this one. Just do it in one video. So now that we know we can send data, we have a couple ways to do this. The main one, the not good one, is probably just setting up well, I guess fuzzing it might work. Probably not, though. I don't like that idea at all. If we look back at the challenge, the real way to do it is to try and identify what we can send and what we have control of. We've already identified some of the commands, so it might be a little bit easier than we're anticipating. But we need to craft a packet that, if sent to the device, will stop the agent process and prevent it from restarting. So we need to do both of these options in one packet. If it's possible in two packets, whoop-de-doo, they don't want that. They want it in one packet. So we need to find a way to do that. So if we go to, we need to find a way to first just stop the program. So if we go back to main, we haven't looked at this part of the function much yet, but we can try and identify what's going on here. We have a couple stuff after our command thread. If you're following along at home and you didn't modify your function, remember we knocked out those two calls, so this command thread looks a little bit, or is alone. Well, that's not really how it works, but so after it calls command thread, instead of actually calling it, it would do it in a thread. We would come down to this do while loop, and we need to identify what this do while loop is doing, because this is going to run in the main thread until it stops. This is actually why I reran. Has that always been there? Huh. Okay, so when we crashed it that one time and ran it back, or started up again, I was confused, and it's actually because of this. So if we look, we just have a while true, so maybe we want to identify where it breaks. Looks like it just returns right here if we can hit this if statement. Down here we have a pthread join. It looks like it's trying to join thread 3. It might be advantageous to us to remodify this file so it has the correct threads, but maybe it shouldn't matter. I don't think it should matter too much. So we have this function down here. We're not really sure what that's doing. We check in here. Maybe there's a system call of some sort. I'm seeing one right here, 7.3. Come over here to 0x73. We have a clock nanosleep, so it looks like it's a nanosleep function. So it looks like it's just on a loop and sleeping. So I might come back here and just name this entire thing nanosleep. Nanosleep for 1, maybe sounds possible. Could just be sleep for 1 second and then go through it again. Pthread join on thread 3. Thread 3 appeared to be what the command thread was. So it's not, so it's just joining it if it exits. We have a function called exiting right here, so that's interesting. So we might want to try and find out how we can identify or get to that. This doesn't appear to be anything. If we look for that variable, IO list reset lock. So maybe it's trying to lock or unlock some printing functionality. IO usually stands for input output, so that's why I'm thinking that. We have some freeze, so it looks like we're cleaning data up. have a function here which cleans more data up. Another function. It's the type of function that looks like there'd be a system call floating in here, but it doesn't look like there is. Not sure what that is. Looks like there's some in-depth ARM function or functionality. Maybe this has to do with threads if we follow the variable lvar4. lvar4 was set up here to set file, so maybe it's closing the log file, so maybe this has to do with closing the logging. Wouldn't be a bad guess besides the fact that it's calling logging after, or what we think. Maybe this is just a fprintf instead of logging, based on the fact that it's printing to 2, which could be standard error. So I would be hesitant to say closing logging, just to know that we don't really need to look into that again. We're freeing a linked list of some sort. Looks like another linked list. Don't care about those. Something about removing a restart file and waiting for other threads to start. So it looks like, and then right here, pointer plus 0x90 is not equal to 1. Looks like the only way we can hop into this if statement. So the main things to notice are this 0x90 not equal to 1 and this restart file right here. We didn't look at it too much, but if we come all the way back, let me open up. Actually, this one should still have it. This one that's running the environment. If we look at start was the original bash script that was run. We can actually see that there's a start agent and restart if it exists. So what it's doing is checking to see if this restart file is here, which it is by default. Then just keep running on a loop if the file or the program dies. And if not, then restart the program. So we need a way to actually delete the restart file, which luckily for us, the program offers us with this restart file function. But what we need to do is get this pointer to 0x94 and this local not equal to 0, which this one should be fine. This appears just to be the actual file name. But what we need to make sure is that pointer at 94 is not equal to, or is equal to 0, and our exit is equal to 0 as well, or some value. With that, we can go back into our command thread, as our only way to really interact with the system is through do command. We can see if there's anything that modifies those values. You may notice very similar values in memory. So like right here, param1 at plus 0x98 actually appears to be very close to that value, or just darn near next to it. The value we're looking for is 0x90 and 94 though, if param1, which makes sense that if param1 is some kind of thread shared object between all the threads and the main thread, or the main loop, that this would just be the same structure. So maybe we're going to try and identify where param is used. Looks like param1 at plus 0x30 is used with the update HMAC key. We had identified that earlier. Param1 at 0x A0 is used. We have this one right here, param1 at 0x90 actually used. So 0x90, if you remember, was the shutdown. So it looks like case 6 is a shutdown functionality. It looks like we have 38, 40, 48 set there, and then that's it. So it looks like we have a way to shut it down. We could maybe run this on loop, or set it to shut it down. A methodology that you could possibly think of is to send a invalid HMAC key that would invalidate all future communications, as the HMAC key has been modified. You wouldn't even be able to successfully get a new HMAC command, as that would be invalid, or all future packets would be invalid. So that is a way to pseudo shut down the system, but it won't actually stop the process from running, as if the process is running, maybe there's a chance that it still spins up one of the other threads to do the SSH server and get a C2 command going, which won't be good. You may have, like the keen-eyed viewer may have noticed the exploit here. We'd actually very briefly covered it in task 5 or 4 or something, maybe even 6, one of those tasks. We had very briefly covered it, and it has to do with the fact that this HMAC key right here. If we remember back, This HMAC key is going to, if we look at it, we have this thunk right here. It's actually really hard to identify what this thunk is doing, but if we dive into it, it's going to be looping. So that's actually not a good way to kind of identify what's going on. But we can see we have a string path, or what we assume is our string, because it's updated HMAC, and then it's written to param1 plus 30. Param1 plus 30 is most likely just our HMAC file, so it looks like right here, open at. Has the open at arguments, and it looks like it does a write, a do while write, so while the length of param3, so param3 is probably our length. We can actually come over here and name these. rvar1 plus 1, which, so this is good chance that this is just going to be a string length. Even though it's showing up as a thunk, it's probably a string length. So what this is going to do is just write our HMAC to the HMAC file, which by itself, nothing's bad because it's going to just copy. It's not going to save anything in the stack or in the heap or anywhere in memory. It's just going to take it from our buffer and send it in. We could actually go back to command thread, and look at where the data comes in, and remember that our data needs to be at least 0x A0 and is limited to 0x360, so there's no buffer overflow there. But we did identify very briefly a buffer overflow in read HMAC key. If you remember, read HMAC key is going to actually use stat to determine how long the file is and read it all into a buffer. Pointer is just used for, it's actually where it's reading it into, but I believe that should be fine as it's going to use a string length. I think it should be fine. I think it copies it somewhere. Yeah, because if you remember, our HMAC was always in memory at a specific location. So this might not be string length, considering the fact that there's 4 parameters. This might actually be a mem copy of some sort. But as far as we know, the read for this HMAC is actually going to read in arbitrary data. And we had identified that when we had looked at it with our print. We had dumped into our fake HMAC. We could actually probably look at it in memory now. Let's open up GDB. That's our running system. If we go back to 5, 6, 7, 8, where's that one at? This one's an 8. If we look at our temporary HMAC file, we only have a couple A's. But if we were actually to load that guy up with a bunch of A's, we can see what happens. So I'm going to kill this. Kill that. Clear this. Let's echo a bunch of A's. So it just needs, by default, the HMAC was supposed to be 64 characters. So let's do more than 64. HMAC key. Don't really need that terminal anymore. We'll start that up, connect GDB into it. I want to set a breakpoint where it reads the HMAC key in though. Let's go to command thread. We're going to set a breakpoint right at this function call of 4013FC. Not that one. Break at 0x this. Continue. We need to then send some data over a socket. Localhost 9000. TACU 9000. ASDF doesn't matter. We can see we hit here. So it's going to try and read into HMAC into this buffer. If we look at this buffer, we can see data. But if we press next instruction and check it out, we can now see that we overwrote way more than our buffer of 0x60. What did we overwrite? It's a little bit hard to identify right away. But if we look through Ghidra one more time, I think we should be able to identify it. So we knew in param1, oh gosh, I don't like the way they are doing that. That's going to be param1 plus 0x50. Yuck. Actually, that's fine, I think. Param1 plus 0x1a. Because we had the suspicion that within, not decrypt, do command. Yeah, there we go. We had a sneaking suspicion that param1 and do command was our same structure as the original file, or as the original main thread. And if we check here, this is sending in param1 plus 2, which is actually going to be the second element in param as a long or undefined pointer here, but here long pointer. But here we're doing param1 at 2 plus 0x50. So what does that mean for us is the fact that we're now saving into the structure where our reboot and send flags are at. And if we look, where was I looking? GB's right here. I want GDB. If we look, we have 2 1s set right here within the, this would be 50, 60, 70, 80, 90, and 94 spot. And if we remember back to main, the indexes of 90 and 94 happen to line up with what we think are the remove restart file and reboot command. So it appears that if we can overwrite the HMAC, the next command that is sent is now going to kill all the, or not kill the, kill the threads and try and remove the restart file and exit from the system, doing exactly what we want. So now we just need to try and implement a command that will do that. I'm going to kill this just in case all these A's mess something up. So I'm going to go back to Ghidra one more time to try and identify what we're looking at. If we remember, the where's it at? Go to main. The command itself is going to need this just to be not equal to negative or not equal to 1. So there's actually a lot of ways we could do that. We were thinking 0 at first, but 0 might not work because this, where am I going? Go back to Ghidra, go back to do command, do underscore command, command thread, command thread, so not just do underscore command. If we look here, we can't really send no bytes, and that is the reason because case 2 is going to use a string length, and the no bytes won't allow us to send no bytes. So we need to send a value that makes it larger than 1 when we overwrite it, which is possible. But what about the no byte we need to send for the second parameter? Because that in main needs to be set to 0 exactly. Lucky for us, it is currently set to 1, which makes it easy to overwrite with a no byte. But now you're thinking, hold up, you just said we can't send no bytes. But there's one more functionality of this file that we missed, and that is not this file, this command. And that is the fact that it's not only taking string length, it's taking string length plus 1. So it's actually going to write one extra byte past what we're expecting. And that right there is the key. So with this, we can actually test it out. So it appears that all we need to do is send a file that is 0x48 characters in length, 4 more characters to overwrite the kill flag, and then 1 no byte to overwrite the reset flag. What is the best way to do this? I'm going to run this. I'm going to actually modify our HMAC first so it can correctly... I actually don't want it to send an HMAC. Here, actually, let's do this within... We have this fake environment running this entire time, and this would actually be a perfect spot to do it. So I'm going to edit a HMAC key file, or echo actually tech n, HMAC key. No, I want to echo that into HMAC key. Our HMAC key, if we remember for our exploit, I'm going to close this one. Actually, copy that real quick. Let me close that tab. I don't want this one either. Echo that into our HMAC key. So if we cat HMAC key, it should just be that file, or not file, that string. Is there anything else we need? Let's check out private. We need to make sure the private key, public key stuff is working. Go back, change to private. Private doesn't exist. Oh, there it is. Private. The private key itself will be empty, which doesn't work. We need to copy ECC public into private. Because remember the... No. Because if we send G, public key was the shared key. So they would still need the private key to get that shared key. Trying to think of a way we could test this out validly or correctly. We could just modify the file again to just ignore the checksum, or not ignore the checksum, but ignore the AES stuff, as we could just try and send a clear text payload, see if that works. But I'm thinking off the top of my head that this itself won't actually be able to decrypt the data we send in, as it won't be valid in the ECC part, in the AES part. So I'm trying to think of a different way we could do this. Granted, we could just set the private key to some garbage, and then when it encrypts, I wonder what happens if we set the public key to, or set the private key to 1. I wonder if that would work. Because then when we send, instead of sending G, we send the public key just for this test case. That could work. I think it might be easier just for us to send a garbage key. And then that way we will still have the shared communication. We just have to, just for our test case, we'll have to do a little modifications. So I'm going to copy the public key into the private key. id.text doesn't actually matter because it doesn't use it in this case. id ed25514 shouldn't matter. Agent restart. I think everything should work if I run the start command. Let's run start and see. That's fine. Actually, I should have ran that in the background, but that's all right. Can I kill it? Let's run start in the background. ps-ox agent should be running. Perfect. So if we kill agent, kill 1655. After a couple seconds, it should just start back up again, if that even kills. Kill tech 9, 1655. I think it should take, depends on what we were on the loop. No, it should take 10 seconds. There we go. We can even do a netstat to figure out what ports are listening. So port 9000 is listening, so it looks like agent is up and running. Let's make a little test script to send our payload now. I'm going to, I'll leave this one, because that can be our, I don't think I actually need that anymore. I'll close this. Don't think I need that one. Don't need GDB right now. So this guy, we know what we want to send. We want to send command to restart the, not restart, but to overwrite the HMAC key. So if we go to case 2, we want to send case 2. I want to send this with one parameter. Down here should then be our HMAC key. It looks like we have plenty of bytes, so we don't actually need to worry about the AES stuff later on, because we have a decryption key up to 0x80 bytes, and our payload, as we had counted earlier, really only needs to be 0x45 bytes, counting the null byte. So I'm going to move this off to a new line, delete all of these bytes, make this a little bit easier myself. Oops. Yank this. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. That should be 1, 2, 3, 4. Should be a 0x40. 4 more bytes. Should get, oops, didn't want it there. 4 more bytes should get us that. And then 1 more byte for the null byte. Setting this to 0x100 shouldn't really matter, I don't think. Let's see, am I missing anything? I think I might need the ECC stuff in this. I can go back to the ECC file in 8, because since we modified the shared key, since we set that private key to the public key, will actually be different. I might be able to send it as 1, 1, 1. I'm not really sure how that works within That's worth a try. Just set the public key to 1, 1. Or set the key we're sending to 1, 1, and see when if it multiplies, it gives us the public key back. There's a chance it won't, though, but that's a chance I'm willing to take in this already 1 hour long video. Because heck, what's another 10 minutes of work at this point? This should then print out the checksum if everything is done correctly for our data. Oops, GCC gen a.out. Actually, 0x100 is going to be too much. So it's 0x40. There's another 0. Oh, 40, 40, 40. Technically, this one, I guess, could be appended or sent out to 40, so maybe it's fine. We'll just append it, or we'll set it within our script. So OC, I'm actually going to change this so I can easily copy this into a Python script. We'll add \x, change this to a comma. No, get rid of that space. So I should be able to copy this into a Python script very easily. I'm going to make a script decrypt. We'll send.py. Checksum is equal to this byte string. I accidentally copied a bad character in there. We'll do the key. We'll do public key is equal to the byte 0x0 times 0x3f plus bytes of 1. Will this work? In my head, it's screaming no. But we're going to try it anyways. I'll just copy that twice. This way we can set x and y to 1, which I think we need to do. Not actually sure on how that works with limited elliptical curve. There's a good chance that this isn't even how elliptical curve works, and I'm just making stuff up. We know our data is within gen, so I might just copy this print down here at the bottom of gen. Close this file. Set this to 0x100. Set this to AES data. The problem we have right now is this isn't our actual data. We need to AES encrypt this. I'm going to copy that for now. Come over here, go back to 8. Actually, did we even use AES in this one? We did not. Yeah, we erased all the AES stuff. Come back to 8, agent code, vim, test.c, AES here we we did stuff here. So I'm just going to actually modify, let's not modify this file. Let's copy test.c into create.c. We'll just do it in this directory. Getting too lazy to move everything over. Temp buff is what we want to encrypt. I'm just going to set it here, unsigned char temp buff at 0x100 is equal to this string. We have all of our A's, we have some more null bytes at the end, perfect. Which means we don't actually need any of this anymore. Public key, we'll keep that because we still need that. SHA-256 it, CTR, that stuff. It's literally just this part. Oops. Temp buff, change this to 0x100. Int 0x100. We'll do \x again. This way we can print it to... Oh no, does it have the commas? It doesn't. Oh, I didn't set the commas. Nice. Does it have double? Oh, okay. Just something looks off. Maybe it's just all the zeros are hypnotizing me. Don't care about this print. I think that should be it. Let's go GCC test. Change chest to create. Create.c, please. A.out. Looks like we have some AES data. At the moment, it's a little tough for us to determine whether this is valid without just sending it. I think I can close that file for now. Let's go into send. So this is where AES is equal to this data here. The checksum is fine because that is done on the decrypted data, not the encrypted. Public key checksum AES. That should be everything we need. We can check the length to make sure it's valid. So final packet is equal to checksum plus PK plus AS. I'm going to print the length of final just to make sure this lines up. Also print it in hex. If this is 0x100, this should be another 60, so 0x160, I think. Oops, I had GCC Python 3 send. PK, oh, this one's a string. That's not how that works. So 0x1a. Where did we go wrong? Oh, no, this is going to be more than 100. This should be 140. Plus 60 should give us 1a. Yeah, that lines up. Okay, so from Pwn Tools, from Pwn import everything. Just using the Pwn Tools library to connect to it. P equals, let's actually make sure our tep is still set. It doesn't look like it is, so we're going to have to set that. ifconfig. Set that to a valid IP. Can we hit the box 101.255.254? We can. P is equal to remote at this address on port 9000. Need to set UDP. UDP equals true, question mark. Might have to Google this real quick. Yeah, I'm just going to run it, see if it works. P dot send line, not send line, send final. Now, if everything works in this test, we should be sending a, well, if anything doesn't work, it's going to be this. I'm not really confident in that being a valid solution yet. Doesn't know what UDP is, which makes sense. We'll go Pwn Tools, UDP socket. UDP. Oh, type, TYP. Set TYP equal, not try, equal to UDP. Let's try that. Spell type correctly. So it set the data. We can check back over here. As it might have gotten a file. If we check out HMAC key, did it correctly overwrite it? It did not. So it doesn't look like that actually worked. Oh, I could actually modify the config to be verbose. That would actually help us. Let's do a quick edit to start. Not start. VI config. We're going to come over here, set this to 0. I was wondering why it wasn't printing. I totally forgot about this. We need to restart agent again, so we just kill this. And just wait for that to start back up. Any second. Okay, it's back up. We'll check the port to make sure that got instantiated. Appears to have been. Okay, so now if we... Actually, it's weird that when it started back up, it didn't give us logs. Because the config was modified, wasn't it? And the restart file shouldn't have made a difference. We can try running our command again, see if it prints. Did not print anything. Restarting start shouldn't do anything for us as... Yeah, so restarting start shouldn't do anything for us as it's not printing anything. I might modify this so instead of start running, I can just run the binary myself. Oh, could be because it's daemonizing as well. daemonize is set to true. Let me try changing that as well. Config daemonize false. PSOX, kill this again. PSOX. I might just kill start and run it myself. Run the command script myself as it makes it. Oh, there we go. Okay, that time it did start up. It's going to be failing to opening these temporary sockets, but that's all right because we're not going to be using the nav process or in the other operations. So it looks like it received 416 bytes, but it did not successfully get to the command stage. The command stage should print out that it got this command at this part. So that means that the key right here functionality did not work, which is all right. We kind of assumed that. So all we need to do is then set this, since it's a public key, all we need to do is set this ECC part. Just do a quick ECC command to see what it's actually the value should be. So SHA-256 update ECC. Where are you at? Am I even calling you anymore? I think I stopped calling you at some point, but I delete it? So it looks like we reversed. It could be that I also put it in backwards. If I put it in backwards, it would be byte at 0x01 plus that. That's worth a try while we're here. Oh, I can actually leave that one. Just delete this last one. Get this guy open, see if it reads the bytes. Okay, still didn't decrypt them. So that key, that's apparently not how elliptical curve cryptography works. You can't just set this to the byte 1 in X and Y and hope that it returns the same key back. But that's all right. So if the public key is what theirs is and we send it G, that should give us something. Public key. Let's actually change this to G. And then we'll set the public key right here to that. That should possibly work. So I'm going to go G underscore curve. G underscore curve. I think that should work. It might be worth just copying those bytes into something else, but I can't be bothered at the moment to do that. Mem set the p.private key. Change this to a mem copy. Private key to the public key. I'm not sure what the SHA-256 is doing right now then. I think I might just comment this out and then ignored it for now. Because that's not needed. Up there at least. It's going to be needed later, but just not right there. We set view random, ECC point and multiply, and then we print out the point of X. So this should give us our key that's used. Oh, GCC, ECC. G curve is undeclared. Is it curve G? Yeah, curve capital G. There is a chance also that I'm not sure if no, it should be commutative since it's just multiplication. That you might just be able to. I could have left this as public key and put G right here, and then all it does is. We'll try that. This is just for, at this point, this is just for me. I want to see if this works. Curve G plus 32 did not like that. Oh, it's a point. I can do G.X. I think I want the address of G.X. And the address of .Y. Appears to have done something. Segmentation fault, so that definitely didn't like that. Well, let's go back up to the top, see what we can do with these. Oh, these are static. Okay, we're going to have to copy those into memory. Char G curve. Here, I'm going to undo all this first. Char G underscore curve is equal to 64. And then we do a mem copy at curve underscore G into G curve. We'll do 32 bytes dot X and then G curve plus 32 into y. Do I need to reverse the curve? I don't think I do. Still segmentation fault? Oh, I'm not even using it right now. I didn't set it down here. So let's get rid of private key. Get rid of this parameter. Set this to G curve. Segmentation fault. Should return L.product. That's fine. Okay, I think I'm going to pause the recording as it's getting long. Just try and get a working solution, and then I can jump back in and explain what's happening. So, be right back. Alright, we're back. I don't know if you'd noticed, but I made a bunch of mistakes while writing this. First off was the public key was too big. For this testing, I just straight up changed it. I'm going to set a public key to 1. I had the checksum and public key in the wrong order. I think that was kind of the majority of it. I've probably noticed that the AES key changed entirely. That's because the public key changed, which in turn made everything else change. For some reason, the ECC script wasn't working at all. So I just instead ran it in GDB, because if our script doesn't work, we can run it in the same place that's going to be running on the remote server. Probably the best way to have done it in the first place. And I could just copy the bytes over. My hypothesis is that because the private key won't be the exact same, since this is normalizing based off of n, that's going to be wrong. I thought VLI add would work, but this functional or this library didn't have the, as far as I know, doesn't have the same functionality to make that interact correctly. So I just ignored ECC. Going into create, I then just hard coded what GDB gave out as GDB val and copied it into what were SHA-256 right away. So just copying in there. I copied it before the reverse function happened within the ECC library, or ECC functions within the binary. So I got to reverse it. Then after it runs, able to get a blob, which I can dump into our AES. So yeah, so now we should have our private key or public key, which is going to be using on the equation, our checksum and AES, and then if everything works, our remote instance should have it going. So if we check set HMAC key to the secret, private key currently is set to all ones, just to make it easy on myself. I tried setting it to the public key, whatever, but I gave up before I figured out what I was doing wrong. I was like, I already have ones halfway written, I'm not going to go back. If we check PSOX should be running agent with our start, so if agent dies, start restarts it. So if we send our command, have it interactive so I can make sure I'm interacting with it. Looks like we update our HMAC key. This time it's all ones. If you wait a little bit, nothing's going to happen. That's because if you remember, the HMAC key is only read when the next command comes in. So if we go to command thread, after it happens after it reads from a socket. So we have to send another packet to actually interact with it. Okay. And then we can see that it received another byte. Now it's stopping upload, stopping collect, waiting for other threads, removing restart file, starting command thread, exiting. And if we check command file is done, and then the script stops after it finishes its next timer. So it looks like locally that works. Now we just need to finalize our payload for the remote. The only thing that should really be different is the AES and the public key. Those will both be different. I don't need this tab anymore. So coming over here into create, I can now get rid of this stuff because now we want a SHA-256 on our public key, as the public key is what's going to be interacted with because of the incorrect key generation. So public key, I think that should be good for our AES. GCC create, run that, copy this guy over. So I might even just make a note, testing with one's private key and public. I'm going to make that ampersand. Alright, we make this real. Public key is equal to, we're going to set that to the G curve at some point. But for now, AES is equal to that, which I should have. I copied all the bytes. Delete that. We don't have to worry about the checksum because the checksum is based off of the raw bytes when it's decrypted, and we have not modified that once, so the checksum should always be the same. G-curve, what would be the best way? I think if I come in here, because I don't want to send it backwards. Oh, I can just copy it from the raw packet, actually. That'd be the best way, as it already has it. So let's just read it in. F, well, it's equal to open, are we in the code directory? We are, so .1.raw. I'm going to read bytes. Then we're going to only take the first 0x40. I think at first I was taking 0x40 for each the x and y coordinate, and that's not correct. It should be 0x40 together. So that should give us our public key, as it's always going to be the same across any packets. We have our checksum because our bytes aren't being changed, and then we have an AES encrypted packet. This is pretty much going to try and connect to the remote instance, which doesn't matter. So I can exit here and just do with open final. Actually, no. Let's just print it. Print final, because we have to paste anyways. Hex. Send.py. It did not like this because I've got to read first. So this, in theory, should be our final payload. I'm going to take a quick look. 6B17, that does look like the G17 that we had saw earlier. Open up the wrong tab. So we come over to the Codebreakers. I'm going to refresh the page anyway, so I'm just going to refresh it now. It wanted the byte stream in hexadecimal without IP or UDP, so this, in theory, should work. HMAC failed to validate. Interesting. It shouldn't have occurred, as we had seen in our previous example that HMAC did validate. Did I mess up the HMAC somehow? The HMAC was set to our key. Oh, right now it's overwritten because I was testing. But should be secret key 88538, which should be hard coded within our create script. HMAC, where are you at? HMAC doesn't actually happen here. It would happen within this script over here, within the gen.c file, which I have open somewhere else. Secret key HMAC 88538. I'm going to print that just to make sure. Oops. GCC gen. Secret key 88538. Did I just not do enough bytes with the AES? I think AES should be, or AES might be hard coded to a number of bytes, and I might have gone through as enough. Does it 0x100, which our payload should be 0x100. This should be 0x100, so that should be fine. The HMAC itself should create a what does gen do? I'm printing AES data. Let's print up buff 32 characters. Oh, that's because we had modified it to make it easier for the Python script. 0C, that should all be the exact same. Send. Okay, I'm going to have to pause the video one more time to figure out what I messed up, because this should work. 1 second. Alright, back on this. It took me a little bit longer than I was hoping to hopefully find a solution, but I came to the conclusion that looking at our AES encryption, this is the old one that we were using that came up wrong, is probably not right. For some reason, and I couldn't really figure out why. I didn't look too hard though. Is that the script I was using to create the payload? Well, now it's all 6 ones, but that doesn't matter. I was doing some testing. Wasn't actually generating the correct output, and the reason I could determine that was by the fact that if we remember back to when we first started this challenge, the packets that came in both had the same XOR cipher. And what's the point of us trying to reinvent the wheel when we can just reuse that XOR cipher and dump out our payload? So I just, in the same Python script, decrypt.py that we were using earlier, I just recreated the payload. So this is actually wrong. That should be 20 or 68 ones. 2 times our 0x 40 bytes there, 0x 40 bytes there, and then our HMAC, new HMAC, 61 or 68 ones to overwrite the restart flag, and then 1 null byte, or in this case, 3F is wrong as well. That should actually be 4 minus 3F, or 40, so 3C, I believe. Because that should be 0x20. Oh, no, that'd be 0x20. And then 4, so I need to go another 20 down, so 1C. I think that payload should be an even hex, so the length of payload on an even boundary. E0, that is not an even boundary. 40, 40, and this should be 40, 0x40, oh, it's 64. Yeah, so this should be 3C, I was right. Python 3 decrypt, please. There we go, yep. So it's an even 100 boundary, and this should be our payload, and this looks more in line with what the offsets should look like. So if we do Python 3 send, in theory, this should now be the payload that gets us the correct exploit. And there it is. So that was the problem. It turned out the AES encryption that I was using with the script was actually incorrect. I'm not sure I spent so much time even trying to implement it like that when we should just use the XOR cipher. So just a quick recap of what we went over. So we were able to decrypt the 2 packets, the 2 raw files, by the fact that since they're both using AES-CTR method, that they both had the same XOR cipher, and we were able to guess what kind of packets they actually were. This in turn gave us the XOR cipher entirely for all packets and allowed us to implement that XOR into whatever packets we created, and then we were able to determine that there was an exploit in the fact that if you read in an HMAC of size 0 or size 68 bytes, it would overwrite not only the restart flag, but the delete restart file, or the exit flag, but the restart file. And this allowed us to then send in the packet and shut down the system. And that should be everything. If you sticked it out through this challenge, I know it's a little bit longer video than the others, thank you for watching, and hopefully you learned everything across all these challenges.